In this lecture, or sequence of lectures, we're going to talk about calculating surface area, and specifically the surface area of a object that we create by revolving a curve about either the x-axis or the y-axis. And when we revolve that curve, we get a surface. We may get a solid, but we're thinking about the surface of that solid. So let me begin with an illustration. And we'll start with a curve. So you see our curve here, and of course we're interested in the curve from A to B. And let's assume that curve is defined by the function f of x, or the function f. So that's the curve we're talking about. Now, let's imagine rotating that curve about the x-axis. And then let's imagine what type of shape that we would have. I believe we'd get a shape something like this. Now, regardless if this is a solid or just a surface, and really in this case it is just a surface because we're revolving only the curve about the x-axis. We're not revolving a region, an area about the x-axis, so we do just have the surface here. Now, we're going to do this in ways that we've done in the past. What we're going to do is we're going to break this curve into little pieces. And then we're going to be able to decide for that little piece that we rotate about the x-axis, if we can calculate the area of that, the surface area of that little strip that we have. And so let me kind of imagine it in this fashion. Let's go over to our curve, and let's imagine that we've got a piece of this curve right here, and so I'm going to try to make that bold so I can see it on there. And of course, the way we're going to do this is going to be infinitely small. But of course, I can't draw infinitely small, so I'm drawing it as I do there. Now, imagine over here on the rotated portion of this, so that would be roughly about this part of the curve, okay? Now, imagine when we rotate that part of the curve, and since this is infinitely small, we can almost think of that as a line segment, a straight line segment, as opposed to a curve. Now, let's imagine that rotating about the x-axis, and we'll concentrate on that piece of it. Okay, I've tried to illustrate that situation here. And I hope that this fits the bill. So as we look at what we've got, then here's the next thing that's going to happen, is let's take that piece and let's look at it alone. And so I'm going to maybe expand it. We're going to have something that looks like this and looks like this, and as we think about the pieces, okay, now remember, so we have a strip like this, and here, okay, and here. Now, this is called the frustum of a right circular cone. This is called the frustum. Frustum, of a right circular cone. Here's what happens, and what this is a piece of a right circular cone. So let me just mention to you, of course, what that is telling us, that if we had a cone, right circular cone, of course that means the base is going to be a circle, okay, and then we have something that looks like this. Now, a frustum then is when we take out a part of the cone. See, we just kind of slice out a piece of the cone, and so we would have something that looked like this, and that's our piece that is in a vertical orientation rather than a horizontal orientation. Now, what we're actually going to do in developing this model for us to be able to calculate a surface area is that we're going to imagine that this frustum is actually the base of a cone, a circular cone. So we're really imagining this scenario where the frustum that we've got is maybe at the lower edge, if you will, of this right circular cone. I mean, the lower is the part of the base. So we're starting our cone there. Now, here's the issue. We need to know the surface area of this frustum. Of the frustum. And then we're going to use, I keep misspelling that, frustum, excuse me. And then we're going to use calculus to add up this surface areas of all the frustums that make up the surface we're interested in. So, add, and it's an infinitely add, isn't it? To infinitely add the infinite number of small frustums. Infinitely small frustums. We've seen this idea before when we were actually doing arc length, when we were doing area under a curve, area between two curves, and so on. And when we were doing volumes based on rotation, using the shell method or using the disk method. Okay, so the surface area of our object that we're interested in will then be an integral, and we'll start these frustums at A, and go to B, and this will be the surface area that we're adding up of one of those. So we're adding up all of them. So we're adding up the surface area of all the frustums we can get. So that's what we're going to set up. But this takes a little bit of work because first we've got to know how we calculate the area of a right circular cone. So this is going to take us a bit of time. Okay, we're going to now calculate, and this part of our job is to calculate the surface area of a cone. So let's imagine a cone first, and of course a cone, a right circular cone, I should say. So let me get something down here that we can refer to. Now, of course, the base of this cone is a circle, and let's assume that circle has a radius of r. And let's imagine if we measure up the side of the cone, the measurement of that side we'll say is L for the length of the side, okay, as we measure from the base to the tip. Now, let's imagine cutting that cone with a pair of scissors. We'll say we'll cut it, right down here. Well, I guess just like this, cut it right there. And then let's open it up. Now, when we open it up, let's imagine what it's going to look like, okay? This cut edge is not going to fit together anymore. So let's say that this is one side of the cut edge, so this length right here is L, and this is the other side of that cut edge, and when we open it up, we're going to get a circular shape out here. Oops, well, that's kind of ugly, and my bad there, my bad. That's supposed to be circular, unfortunately. Now, we happen to know the length of that curve, see, because the circumference of the base, the circumference of the base here in the right circular cylinder, the base being a circle, and the radius of that circle is r, so the circumference is 2 pi times r. So that's this distance. That's called an arc length. See, that's this distance around here, because that's really all that base. All of this distance around here is 2 pi r. Now let's assume that this angle is an angle theta. Okay? Now, what we're really looking at here is a sector of a full circle. Part of a full circle is called a sector. And we're looking at part of a full circle. Now, what we would like to know is the area of that sector. So the surface area of the cone, okay, the surface area of the cone is equal to the area of the circle we see there, the sector. Now, in radian measure, okay, the area of this sector, and that's what we're looking for, the area of the sector is only a fraction of the area of the entire circle. Now, what entire circle am I talking about? I'm talking about the circle of radius L. See, if we come up here and look at this diagram and continue that around, we would have a full circle whose radius is L. So this sector is certainly just, the area of that is just a fraction of the full amount. And what fraction is it? I mean, it's the same relationship as the arc length of the sector. Okay, the arc length of the sector is to the arc length of the full circle. Okay, that is the measurement all around. And of course, the arc length of the full sector of the entire circle is just the circumference. And so the circumference of the circle we're talking about here is 2 pi times its radius, which is L. And so what we end up with, of course, the arc length of the sector was defined earlier, because that was the circumference of the radius of the cone. And so that's 2 pi r, and the arc length of the circle, or the circumference of the circle, is 2 pi L. Okay. Now, let's look at what this gives us. We have the area of the sector, which is what we're looking for. The area of the sector. That's what we're looking for. Is to the area of the entire circle. Well, what is the area of the entire circle? Well, it's pi r squared. So in this case, it's pi times L squared. That's the area of the entire circle that we're talking about right up here. Okay, and that's equal to 2 pi r over 2 pi L, which is r over L. So we have the area, now we're going to multiply both sides by pi L squared. So we have the area of the sector, which remember that this is what we're talking about, the area of the sector, which is the same as the surface area of the cone, because we split that cone open, and this is what it looks like when we split it open. So the area of the sector is equal to pi L squared times R over L. And that simplifies to what? Pi, I'm going to write it in a little different order, R times L. So now as we refer to the cone, the surface area of a cone of a right circular cone, I'm not writing that in, is equal to, now refer to the diagram, is equal to pi times the radius of the base of the cone, which is R in this case, times the edge length, that is the measurement along the outside of the cone from the base to the peak or the vertex. As we're referring to up here, these are the R's and L's that we're talking about. So that's how we calculate the surface area of a cone. Now, how does that fit in to what we're going to be looking at? And that's actually the area of a frustum. Of a cone. Okay, well, we'll pause here and go to the next page. But what we're really going to do is, well, let's just go to the next page. Well, I've set up a couple of diagrams here, and maybe I should have started with this. This is a frustum, and we want to know its area. Okay, surface area. Now, what I've done is I've created a diagram here with a cone, and this is the frustum that I've drawn over here on the side. So we want the surface area of that frustum. Sorry, I'm having trouble with that strange word. I don't use it often. Now, what we could do here is if you can imagine, we can have a little cone, which is from, we'll say, from the origin to this position, and then we can have a larger cone, which is the origin to this position. Okay, and I've actually drawn that first mark in the wrong spot, but that's all right. So to this position. So let's talk about this of this big cone. Then the radius of this big cone would be here. Okay, and so this radius we'll call R sub 2. And then the radius of this smaller cone would be here. Okay, and we'll call this radius sub 1 just because it appears before the radius 2. Now, well, let's go with this. So, okay, I've drawn a cone that is, of course, horizontal in shape, and you can see that the frustum I'm talking about is this frustum, which is more or less the base of the cone, not the base, but a lower portion of the cone. And we'd like to calculate that area. So imagine that where A is, from the origin to where A is, we have a small cone. And from the origin to where B is, we have a large cone. So let me point out what we're going to do here. The area of the frustum that is shown is going to be the area of large cone minus the area of the small cone. Well, let's talk about the area of the large cone, and let me refer to the radius, okay, of this large cone as r sub 2, okay, so we'll let that be the second radius, and the radius of this small cone is right here, okay, and that radius we'll call r sub 1. Now, let's suppose, obviously, the edge of this cone right here, the edge, we can think of as, well, of course, it's a straight line, and so it has some equation. Now, it's a straight line, and it goes to the origin, so the y-intercept is 0, and so this could be described as y is equal to some slope times x. Now, usually we would say m for slope, but for the purposes I'm going to use here, I'm going to call that c. So the slope is c. So that's the equation of that line that we see there, or that portion of the line. Of course, the line extends. Now, if I keep that in mind, then this radius is the radius at the value of x, where x is b. And so this is actually a y value. Okay, it's a y value for b, and it's the y value when x is b. So r sub 2 is equal to c times b. Now, likewise, over here for this r sub 1, okay, let's kind of come clear around this r sub 1. Well, this r sub 1 is also, we can think of it as the height, the line is there, so that's a y value when x is a. And so in this case, r sub 1 is c times a. Now, for the purposes of okay, let's talk about the area of the large cone. Okay, area of large cone. Well, remember how the area goes. It's pi times the radius of the base times the length of the edge, okay, times the length of the edge. And I need to be careful here because I'm going to be reusing some of these values. And of course here, the radius is r sub 2. And we've already decided that's c times b. And the length here, well, I haven't really named that. So the edge is all along here, and so that length, I guess we'll call L sub 2. Okay, so that's actually L sub 2. So what we end up having here is pi times CB times L sub 2. Now, let's come in here and let's just look. Let me kind of concentrate for a bit, if you will, on what we have here. I'm not trying to make this exact, but let's not look at the 3 dimensions. Let's look at the 2 dimensions. So this is where B is. This is L sub 2. And this is that other side, which we decided because the equation of that line, this side is CB in length. So this side is B, this side is CB, and of course the hypotenuse of the triangle, that length of the edge, L, is L subscript 2. So L subscript 2 is really the hypotenuse of a right triangle. And so L subscript 2 will be the square root of the sum of the squares of the 2 sides. Now the 2 sides are CB and B, so we'll square side the side CB and plus the square of side the horizontal side and the vertical side, we see. First the vertical side, then the horizontal side. But look what this tells us. L sub 2, if we square CB, we get C squared, B squared, and then plus B squared. And notice that B squared is a common factor there. So when we factor B squared out, we can actually take the square root of it and get B. and what we're left behind with is the square root of c squared plus 1. So L sub 2 up here is really pi cb times L sub 2, which is b times the square root of c squared plus 1. And so the area of the large circle, the large cone, is the square root of cb squared times the square root of c squared plus 1. Now, the area of the small cone, the area of small cone, well, that's pi times the radius of the small cone. And we've decided from above that the radius of the small cone is c times a. And we haven't named the edge, but we'll name the edge L sub 1. So pi times the radius of the base times the length of the edge. Now, let's in the small cone, this is very similar to what we just did above. In the small cone, of course, we're not going quite as far. We're going out to where A is. And so let's look, of course, this is only in 2 dimensions. This is that edge, whoops, L sub 1, okay, L sub 1. And this length of this triangle, okay, is A. We set out to A. And of course, the height of this right triangle is, because we know the equation from above, this is actually c times A. That was the radius 1, okay, as we've seen there. So, kind of like above, well, L sub 1 is the hypotenuse of the right triangle. And so it's the square root of the sum of the squares of the sides, which ends up being, in this case, a times the square root of c squared plus 1. So we put that back in here, and we end up with pi times c times a squared times the square root of c squared plus 1. But we're making some progress here. So, the area of the frustum. The area of the frustum. Well, I'm not quite ready for that area. Now, let's go back and look at the frustum. And remember, it looks something like this. I'm exaggerating. Now, the frustum, of course, is the shaded region that we've got way back up at the top. And if you will, the edge of this frustum, the edge we'll call L. Now, let's think about up at the top. Of course, this is where A was. Remember, this is the A value, and this is the B value. Okay. Now, let's look at this frustum, and let's look at the right triangle that it would create right here. So let's just look at that right triangle. It's up in the air, of course, and kind of give us an idea. We've got a right triangle where the edge of that frustum is the hypotenuse of that right triangle. Now, this base that is horizontal is b minus a. See, it's the highest x values minus the lowest x value a. The highest is b, the lowest is a. And you can see that over here in the diagram that we've got there. Well, now, what is the height of this rectangle? What is this vertical leg size? Well, remember, look up above. R sub 2, the entire height is the c times b. And then, see, we're talking about this triangle right here. This is the triangle that we're talking about, right up here at the top. You can see me sketching that in, I hope. And so, we're really looking at the difference of the two y values, of the two radiuses. See, this is actually radius 2 minus radius 1. But we already decided that radius 2 was CB, and radius 1 was CA. And so this vertical leg is CB minus CA. And so from that information, we get this hypotenuse is the square root of the sum of the squares of those sides. So we'd take CB minus CA, and we would square it, plus B minus A, and we would square it. Now, a little algebra here. In this first expression, what we could do is factor out a C. So we'd factor out a C, and we'd be left with B minus A, but all that's squared. And of course, here we have B minus A squared. Now, notice in that first expression, we have a product of C and B minus A. So that would actually be the square root of C squared times B minus A squared plus B minus A squared. Now we have a common factor of B minus A. So we can factor out a squared, but we can take the square root of that. So when we take the square root of B minus A squared, we'll get B minus A. And what's left inside the radical is simply C squared plus 1. Well, that actually, so now remember, L is the length of the edge of the frustum. Well, let's go to the next page, and then I think we'll be close to getting our formula. But we're going to need to remember what these pieces are. So I'm going to write them down on the next page. Okay, haven't reproduced the diagram very well, and I apologize for that. But here is more or less the idea, is the area, and actually it's surface area, isn't it? The surface area of the frustum is the surface area of the large cone, okay, minus the surface area of the small cone. And we discovered on the previous page the surface area of the large cone is pi times C times B squared times the square root of C squared plus 1. And of course, likewise, the area of the small cone is pi times C times A squared, times the square root of C squared plus 1. Now, we notice that we can factor a few things out. So notice here that I'm going to factor a pi times C, that's in both terms, out. And I'm also going to factor a square root of C squared plus 1 out, but I'm factoring it out on the other side. And so what I have left in the middle is B squared minus A squared. Now, B squared minus A squared can be factored. We've got plenty of room, so let me come over here. So we have pi times C, and we'll factor B squared minus A squared as B plus A times B minus A times the square root of C squared plus 1. But on the previous page, we decided that this was actually the edge, the measurement of the edge of the frustum, as I've described above. And so what we end up with is pi times C times B plus A times the length of the edge of the frustum. Now, if you recall, actually, let's multiply this C through there. This is actually then CB plus CA times L. Now, CB times plus CA, well, remember CB was actually this radius. See, it was actually this radius. We called that radius 2, and we decided that that was CB. And remember that we called of this frustum, this is kind of the top of this frustum, that's the small circle, okay? And we said that radius was R sub 1, and we decided that was CA. So this is actually pi times R sub 2 plus R sub 1 times the length of the edge. And so now when we want to know, the surface area of a frustum, and that's what we've got here, well, just think about what these pieces mean. So if we've got this frustum, See, it looks like this shape. We'll just kind of put it down on the side. It's part of a cone, but it's not a whole cone, see? Oops, that goes across there. And so what we've said is all we need to do is add together the two radii. So one of these has a radius R2, and one of these has a radius R1. So we need to add two radii together. That's what we've got here. And then we need to measure this edge, okay, the length of this edge, which is L, and multiply it by pi. So we've got a way to calculate now, finally, the area of a frustum. Goodness, this was a lot of work, wasn't it? Now, we need to put this back together on how that helps us find a surface area formula. So let's pause, let's shake things off a bit, and it's probably a good idea to pause the video now for you. And I'm going to start up on a new page here in a couple of minutes. And to you, it will be immediate. So I'm just going to be quiet for a moment and let you shake out your cobwebs. As we go back to our original purpose in all of this, is we're trying to find the surface area of a surface that's created by rotating a line, a curve, about either the x-axis or the y-axis. Now, we've shown, of course, rotating it about the x-axis. And that's normally what we actually are going to be doing. Now, we decided what we were going to do is we're going to break that curve into infinitely small pieces, and that's this bolded area that I've got here in the curve on the first part, okay? Now, when we look at the entire surface that's created, if we look at just that particular line segment, and it's infinitely small, so that line segment is basically the same as the curve itself, then we get a frustum. And so if we can add the surface area of each of the frustums we can get by breaking that curve into infinitely small pieces, and then we add those up using integration, because integration is an infinite sum of infinitely small pieces, then we'll have the area of the surface in question, or the surface area. Okay, so that's where we left things off. That's the reason we went through all of that work. Well, let's look in this case then how we calculate the area of a frustum. Well, that would be what? It's pi times the sum of the radii here. Okay, now let's just notice this case. We'll say r sub 2 plus r sub 1, and of course r sub 2 is the radius that's right here. Okay, this radius. And r sub 1, of course, is this radius. And I'm sorry, that radius that we've got wrong there. Times L. And L is the length of that edge. So that's L. Now, let's do a couple of things before we go further. First, I want to think about L again. And so let's go back to the curve and look at that edge where L is. See where that edge is. So this is the question here. So this is that edge, and I'm magnifying it, but there's that edge, L. Now, L is infinitely small because we're breaking this curve into infinitely small pieces. And what we call that, when we were talking about the length of a curve, we call, if it's an infinitely small line segment, we call that length ds. Okay, well, now, we can think of that as being a hypotenuse. Oh, this looks very familiar to us when we were doing arc lengths. Well, of course, the vertical measurement is a y measurement, and so that's a y value, but if it's infinitely small. So we call that dy. And likewise, the horizontal measurement, the horizontal leg, we measure in the direction of x, and it's also infinitely small since the hypotenuse is infinitely small, and so we get ds there. Now, we know from previous, well, we know then that ds, which is actually L, isn't it? ds is the square root of dx squared plus dy squared. Now, we saw previously the way we would do this, okay, is that L, or ds, What did we do before? Oh, we actually factored out a dx squared from underneath the radical. So when we factor out a dx squared, we have 1 in the first position, but we ended up with dy over dx, actually dy squared over dx squared, and we've had that dx squared factored out. So that allowed us to actually take the square root of the dx squared and rewrite the dy squared over the dx squared. So we ended up with ds, if you recall, is the square root of 1 plus dy over dx, which is the derivative of y, is the squared, and times dx. So now we have a replacement for that L, okay? Now, the next question is, what is this r sub 2 plus r sub 1? Now remember, r is a radius, and so that's actually a y value. So we could call it y sub 2, and r sub 1 is a radius, and that's actually the distance. See, this is the distance r sub 1, r sub 2. And so that's a particular y value, I'll call y sub 2. And this is the distance right here. I'm looking at the curve above, and that was r sub 1, which is a y value, and we could call that by y sub 1. So we could call it y sub 2 plus y sub 1. Now, what I'm going to do here is I'm going to think about taking the average of those. So if I take the average of those two y values, that would be y sub 2 plus y sub 1 divided by 2. Okay, I'm just taking the average of those y values. So and notice then we're going to call that average y, and that comes from a particular x value. And it comes from the x value that is right in the middle of those. So there's the x value, and the y value happens to be the average of those two y values. Well, the importance of that, I suppose, is that simply that we could say y sub 2 plus y sub 1 then is 2 times f of x. And f of x is 2 times the y value, but f of x is, in fact, comes from being right in the middle of that frustum. Okay, well, here's where that puts us above. Let's say, now we have a replacement. Remember, r sub 1 plus r sub 2 is really y sub 2 plus y sub 1. And y sub 2 plus y sub 1 we just decided is 2 times f of x. So now we have the surface area, okay, surface area of our object, okay, and a lot of times we'll just put S for surface area, is equal to the integral from A to B of pi times 2 times the y value that's the average of the two radii, but that's f of x, isn't it? Because we get to a y value by evaluating f. So that's really that y value, which was, in fact, y sub 2 plus y sub 1. Okay. Let me stop and think. Yeah. The y value, which actually was y sub 2 plus y sub 1 over 2, is the average. And times the L value, but the L value is the square root of 1 plus the derivative of y with respect to x, which our function here is f of x. And so it's the square of f prime of x dx. And that came from the L. So all of this is the L. And this ends up being the r sub 1, plus r sub 2 plus r sub 1 right there. So we simplify this as simply the integral from a to b, and we'll, rather than say pi times 2, we'll say 2 times pi times f of x, and that's the curve, remember, from above, times the square root of 1 plus the square of the derivative of the curve with respect to x. Oh boy, that was a great deal of work. So let me have a point here. This is something that we need to memorize. Now, I don't know that I mentioned this previously. When we were studying finding the volume of a surface, the volume of a revolution from a curve or an area, we use the disk method, we use the washer method, we use the shell method. And at that time, I think I suggested to you that memorizing a formula there is really going to be difficult. It's not so much difficult, but there's so many possibilities. We prefer just to go through the process of deriving it as we look at each problem. But it's a little different. It's a little more complicated to derive the formula for arc length and the formula for surface area. And so in these two cases, I do suggest that you memorize these. You put them down, you refer to them frequently until you get them memorized, and then you try to wean yourself from that. Well, this is the end of the introduction, which was quite lengthy. After this, we're going to look at some problems. So we'll stop for now and start up again later with some videos of actually doing some problems. Our first example of calculating the surface area based on our formula, as you can read, we're to find the area S of the surface formed by revolving the graph of y equals square root of x on the interval from x equal 1 to x equal 4 about the x-axis. Now, we're not always going to be drawing a diagram, but in this case, it's not too difficult to draw, so let's do that. We'll pause and draw that. Well, I've sketched in the graph of y equals square root of x from x equal 1 to x equal 4, so that's what we have here. Y is equal to the square root of x. Remember, we're going to rotate that about the x-axis, and so when we do, we'll get a graph that looks something like this. So it looks like we have more or less a cup with a hole in the bottom and the top laying on its side, but we're wanting to know the area of that surface. Now, in general, remember the surface area is given by this equation, or this formula. It's the integral from A to B. So those where the curve starts, the x value A, and where this curve starts, the x value B. So in this case, that's 1 to 4, times 2 pi times f of x. And this is actually the radius of a representative frustum. Okay, and then times the square root of 1 plus the derivative of f squared. This is if we're rotating about the x-axis. So we have to kind of remember this part because that's not so clear to us where that comes from, but that is basically the length of the measurement of the length of the side of the frustum. So we're kind of thinking about, we're looking at a representative frustum here, and say right here, and so we would have something that looks like this going through here, and this radius, that is the distance right here along there, that's the radius we're talking about, and that's why that's f of x, because that's a y value, isn't it, at some given x. So this is some given x, and we're letting x move all the way through the ranges, and for each x that we've got a radius for that frustum, and this is actually the length, if you will, of the edge of that frustum, and that makes sense together, I guess, that altogether that would be the circumference times the area. So that makes a little bit of sense how this formula comes together. You can kind of think about it this way, that this is the circumference of that strip. Circumference. Oops, I broke that in two, didn't I? Anyway, this is the circumference of that strip, and this is the width. So although this is not a strip that's even on the sides, it's kind of the idea that if we were to break this, cut this through here, okay, and then stretch it out, well, this is that length of the strip, which is the square root of 1 plus the derivative being squared. That's the length. That's this length right there. And of course, this length is the circumference, which is 2 pi times r, but in this case, that's 2 pi times f of x. So it kind of fits together of what we've seen before, but we had to do a lot of work. Of course, actually, this length, isn't it, is times dx. And so there's a little more to that length right there. It's times the dx. So all together here. So it makes a little bit of sense. Maybe that will help us remember how to set this up. But in this case, our r is f of x, or really just y in this case, which is the square root of x, or x to the 1/2. Now, we actually need to know f prime, okay, f prime of x, or the derivative of y with respect to x. And of course, we know that that's, without too much difficulty, that's 1 over 2 times the square root of x. And we can go through that process. So here we go. Then the surface area is equal it's equal to the integral, from the first x value, well, that's 1, to the last x value, that's 4. And of 2 pi times f of x, but f of x is y, or simply the square root of x, times the square root of 1 plus the derivative squared. Well, our derivative is 1 over 2 root x. And we're going to square that with respect to x. Well, let's see where that puts us. Here we'll have, let's factor out the 2 pi so we don't have to worry about that. We'll have 2 pi times the integral from 1 to 4 of the square root of x times the square root of 1 plus 1 over 4x. Now, we got 2 square roots, so we can actually multiply through, if you will. That is, we can multiply those square roots together by multiplying together the radicands. So this is the square root of the radicand x times the radicand 1 plus 1 over 4x. And that'll simplify. Okay, so now we have 2 pi times the integral from 1 to 4 of the square root of x plus 1/4 with respect to x. And we ought to be able to handle that. Here's what we're going to do. We're going to think in terms of letting u, we're going to use u substitution. So u is x plus 1/4. Well, now, if you look at it that way, we simply have the integral from 1 to 4 of the square root of u, but we got to worry about this dx. But if u is x plus 1/4, then du is simply dx. And so we can do a straight replacement there, can't we? Well, then the integral of, now remember though, these are x values, not u values. So the integral of square root of u is, let's remember that. The integral of square root of u, that's u to the 1/2 power, is 3/2 times u to the, it's 2/3 times u to the 3/2 power. My bad, 2/3 there. So when we do this integration, we're going to get a result of 2/3 times u to the power 3/2. But u was x plus 1/4. And that we're evaluating from 1 to 4. Okay, now we've got a little bit of work that we can do here. We see that this 2/3 being a constant in that evaluation can be factored out. Let's move up here. So as we factor that out, we'll have 2 pi times 2/3, and we're going to evaluate x plus 1/4 to the power 3/2 from 1 to 4. And I've crammed myself in here again, haven't I? So we have a 4/3, 2 times 2/3, so 4/3 pi. Now, when we evaluate at an x value of 4, we're going to have, let's see, 4 plus 1/4 to the power 3/2. And then we're going to subtract what we get when we evaluate at 1. And then we're going to have 1 plus 1/4 to the power 3/2. I think that there's some work that we can do here to make this look a little better. 4 plus 1/4 is 17/4. So here we actually have 17/4 to the power 3/2. And 1 plus 1/4, of course, is 5/4. So here we have 5/4 to the power 3/2. Now, notice in the denominator, and I'm coming over down here to the side, in the denominator, we're really going to have a 4 to the power 3/2, which is the square root of 4 raised to the power 3, or that's an 8. So what we have here is 4/3 pi times 17 to the power 3/2 over 4 to the power 3/2, which is 8, minus, over here we have 5 to the power 3/2 over 4 to the power 3/2, which is 8. And you see we have a common factor of 8 that we can factor out. So when we factor that 8 out, in the brackets, I'm going to change to parentheses, we have 17 to the 3/2 minus 5 to the 3/2. And of course, except it's factored out of 1/8, not an 8, right? And so when we look on the outside of those parentheses, what we actually end up with is what? 4 over 8 to 1/2, so we end up with 1/6 pi times 17 to the 3/2 power minus 5 to the 3/2 power. Now, that's not very satisfying to us. I'm kind of crammed again. That's not very satisfying to us because we don't really understand what kind of that number that is. So I got out my calculator now, and I rounded that. I did the calculations from the calculator and rounded it to 2 decimal places, and I got 30.85. Now, what is this? Well, it's square units because we're talking about an area, isn't it? And I didn't specify the units, but it's square units. So here's the exact value of that surface area, and here's what that's approximately equal to. Okay, let's look at another example on the next page. As we look at our next example, you can read it, but of course I will for you. The curved surface of a funnel is generated by revolving the graph of y equals x cubed on the interval from 1/2 to 1 about the x-axis. Approximately what volume of paint is needed to cover the outside of the funnel with a layer of paint 0.05 inches thick? Well, I guess the first thing to recognize is if we knew the area of the surface, so the area of the surface, and over that area, we want the paint to be 0.05 inches thick, then that's going to be the volume of the paint needed. Now, of course, paint needed. Of course, we're assuming that the units here are in inches. So this is square inches. And of course, this is just in inches. And so the volume will be in inches cubed or cubic inches, how much paint. Now, before you get to giving me a hard time about this is probably a silly funnel size, but it illustrates the issue. It illustrates what we're trying to accomplish. So let me draw just a quick sketch. Again, it's probably not necessary, but let me draw one anyway. Well, you can see here I've got y equal x cubed graphed. That's this curve. And as I rotate it, then I'm going to get something that looks like this. And so that's the idea of we have a funnel, okay? And we want to know the volume of paint required to cover that surface. So again, we need to know the surface area. We'll call that S. And that's an integral, okay? And we're going to start our x values at 1/2, and we're going to go to an x value of 1 in this case, of 2 pi times, now remember we're going to have a representative frustum, okay? And so I'm thinking about here, okay, this is the frustum I'm thinking of. Now that frustum has a radius. And so remember the way it goes, it's radius of a representative frustum times the square root, and actually it's times the width, okay? And it's actually times the width or the length of that edge. And the length of that edge we decided was 1 plus the derivative of the function squared dx. So once again, this ends up being the circumference of that frustum if we were to cut it in two. That's a circumference. And this ends up being the width of that strip. So if we took that frustum and we cut it in two, we cut it horizontally and laid it out, then it would be circumference right here times the length of that edge, which is given by this formula, okay? And again, that's kind of the ideal. Really what we're ending up with is something that looks like this when we cut that, okay? When we cut that, we're looking something like that. And so this is that circumference, 2 pi times the radius, r, and this distance basically right here, that length right there is this square root that we've got there, okay? So once again, in the radius in this case is defined by this distance, which is a representative value of x. I mean, that's a y value, but we have a representative value of x right here. And so it's this distance that we're talking about, which is f of x or y. So that's the idea of how we get our y value. Okay, an x and a y. But our y value is x cubed. So as we start this up, we'll have s is equal to the integral from 1/2 to 1 of 2 pi, and our radius is x cubed, okay, our y value, times the square root of 1 plus. Now we look up here, this is pretty easy for us to do because the derivative of y with respect to x is nothing more than 3x squared. So we have 3x squared here, which is in turn squared. Okay, now we continue. The integral from 1/2 to 1 of 2 pi times x cubed times the square root of 1 plus 9x to the 4th dx. This looks like a simple u substitution. We factor the 2 pi out, and then we have x cubed times the square root of 1 plus 9x to the 4th with respect to x. So I'm thinking in terms of the u being 1 plus 9x to the 4th. And so du is going to be what? 36x cubed dx. And so to get what I need here, I'm going to have a 2 pi. I'm going to have to offset the 36 I need on the inside with a 1 over 36 on the outside, times the integral from 1/2 to 1 of the square root. Now look what I have. I'm going to put the, let's go ahead and go through this. Before long, I'm going to wean us from this. Here we have a u. Okay. And I put my 36 in here, offset it on the outside, and my dx there. So what I end up here with is a du there and a u there. And so I'd have nothing more than, well, of course, 2 over 36 is 1 over 18. So this is pi over 18 times an integral of the square root of u, which is 2/3 times u to the power 3/2. But u is 1 plus 9x to the 4th to the 3/2 power. And I'm evaluating that from 1/2 to 1. Well, let's see what result we get here. Now, with a little bit of work here, and I'm going to leave that to you, here's what I get. I get that's equal to 640 times the square root of 10. Let's see what I do have. Minus 125. All of that's divided by 1728. And it's that fraction times pi. Now, that's approximately equal to, and that's what we're really needing here, that's approximately equal to 3.4522. 3.4522 square inches. Now, of course, remember, the volume of paint needed will be this amount, 3.4522 square inches, times a depth of, okay, a layer of paint that is 0.05 inches. And when we do that, we get approximately equal to 0.17262 cubic inches. That's how much paint we need. Of course, we could have done this a little differently. Like I said in the beginning, this may not be real world in actual measurements, but it gives you the idea of how we would have approached the problem. Okay, we're going to look at a couple more examples here that follow on the next pages. Let's start out with a little summary of surface area calculations. You notice at the very top here I've written S for surface area is an integral from A to B of the circumference times the arc length. Now let's kind of get back into the idea of what I'm talking about. I'm assuming right now that we're rotating. Notice I said right now, rotating about the x-axis to get our surface. And so we're starting our curve at some value A, and we're stopping our curve at some value of B, and that's what we're going to rotate about the x-axis. So we've seen these kinds of ideas before. We've got a shape that looks something like this. Now, the circumference is referring to what happens when we look at a representative slice of this, okay? And well, of course, the edge up here is going to be at an angle, and so we end up with something as a slice that looks like this. And of course that edge is not straight, okay? It's not straight. So we ended up with this idea is the circumference we're talking about is the circumference of that strip or that frustum that I've illustrated there, which we could think of as laying out in this fashion, okay? Now, here's the issue with that. The circumference, this is after I've cut that frustum, sliced it horizontally, and so this ends up being that circumference, okay? This is the circumference. And the circumference is calculated by saying 2 pi times the radius. And the radius is this value right here, that distance. And that's a y value, see, that's a y value. And so we represent that with f of x. And so we end up with our integral is the integral from a to b of 2 pi times our r value of f of x. And then we decided, of course, that this length, this distance right here, this length, that's the arc length. And we've worked several times in the previous section also to calculate that arc length. We use this formula, square root of 1 plus the derivative of y with respect to x squared dx. And so that's where the rest of this comes from. The square root of 1 plus, we could say derivative of y with respect to x, or in this case, using function notation, we can say f prime of x squared with respect to x. Now, this is if we're rotating about, revolving about the x-axis. It's a little bit different, but the same if we're rotating or revolving about the y-axis. So let me pause and get started here. Now, it looks the same in terms of the concept. Okay, here we're rotating about the y-axis. Now, of course, we're going to have a different shape, and so the calculation will be different. But let's assume we have the same curve, just to give us something to refer to. And that curve looks something like this. Okay? And if I rotate this about the y-axis, then I'm going to get something, okay, I'm sorry here. I'm going to get something that looks like this. Okay, rotate about the y-axis. So I want to know the surface area of that shape. Now, I've got the same idea here that if I look at a representative piece of this curve, oh, by the way, this is down here at C, so that's a y value, and this is up here at D, so that's a y value, rather than the A and B we had up here. So that would be the C here, and up here would be the D someplace, representing the edge, the y values of the limits of that curve. Well, if I look at a piece of this curve, then and think of that rotation, it's also going to create a frustum, okay, like this. Now, the circumference in this case, here's the issue, is that the radius is along here, okay? So that ends up being the radius in there, radius, and that's an x value. See, that's an x value. The length of that radius is an x value rather than a y value. So if we have x's defined as a function of y, that means x's are equal to y stuff. And that's not a very technical, that's not a mathematical term, but maybe x is equal to y squared as an example. Then our radius would be defined in terms of g here. So what we would do is we would be starting, let's go back to the surface area calculation, we would be starting our frustums down at the value of C, that y value of C, and we would stop at the value of D. That way, so we're going vertically. We're starting at C and going to D. And we're adding up the volume, the surface areas, pardon me, of all those frustums that can be created there. Well, the circumference of one of those frustums is 2 pi times the radius, in this case, is an x value, or g of y. Okay, and the arc length is going to be similar, but it's going to be the square root of 1 plus the derivative of g with respect to y. See, g prime of y squared. And what's changing is y, so with respect to y. So it will look similar, except that we have different positions. Now we have a function of y rather than being a function of y, yes, instead of a function of x. So we just have to be a little bit careful, but we'll go about it the same way. So just keep in mind the forms. Now on the next page, we're going to do a calculation which is to find the surface of a spherical cap. And we'll use this formula instead. Okay, we'll use this formula because we're thinking of rotation in a different way. Okay, the surface area of a spherical cap, and we're going to assume that we have a sphere of radius r. So let me, in general, talk about the issue here. Let's first assume that we have a sphere, and then we'll set it up so that we can. Okay, so you've got to think in 3 dimensions here. Okay, we have a sphere. Now, a spherical cap is that we're going to lop off, if you will, a part of the top of the sphere. So maybe we're interested only in this part of the sphere. So we're going to lop that off, okay? And so now what we're asked for, okay, is we have this top part of the sphere. Of course, this cross-section is going to still be a circle, but we want to know the volume of that cap. So this is the spherical cap. Not the volume, I'm sorry, the surface area. Okay, so what is the surface area? Well, it depends on several things, of course. So here's one of the things that it depends on, of course. It depends on the radius, and the radius of the sphere is r. So that's down here, isn't it? See, that's the radius of the sphere. That's r. And the next thing it depends on is how high this cap is, and we'll call that distance h. That distance h. But of course, the radius of this circle in the cap is not r because it's smaller than r, isn't it? We've lopped off the top part. We just have a cap of that sphere. So let's think about how we could create that curve, okay? Now, let's assume first, that we have this sphere on an xy plane, except that we have in front of that and in back of that. I'm just this so I can generate it. And so we can imagine that all we really need to do is look at the top hemisphere. So I'm not really interested in what's going down on here so much. I'm interested in what's above there. And so can you imagine that this, now remember, if this circle, if this sphere has a radius of r, think about taking the circle, which would be defined by x squared plus y squared is equal to r squared. And let's just imagine taking this part of that circle, okay, right here, and then let's rotate that about the y-axis, and won't we in fact have that entire upper hemisphere? So maybe all we need to be concerned about is taking this part of the curve, if you will, right here, okay, let me redraw that, taking this part of that curve, which would be right here, this represents this cap, and that's this part of it, and rotating this part, okay, here's the y-axis, rotating that about the y-axis, and when we do, we're going to create that cap. Okay, so we'll create that cap. And that's what we're going to end up doing. But remember, this curve is part of the circle x squared plus y squared is equal to r squared. And that's what we're rotating. Okay. Now, as we rotate about the y-axis, then we're going to create, there's several things that I need to build up here. We're going to create, and if we look at one little piece of this, then when we rotate that, we're going to create a frustum, aren't we? So we're going to create this frustum that looks like that. So we need to decide how we're going to calculate this. Now, remember, this distance right here, from here to here, from the bottom of the cap to the top of the surface, the base of the cap to the top of the cap, that distance is this h that we referred to earlier. But also remember that this sphere has a radius of r. So from this position, that is from this x-axis, clear up to this position, that's a distance of r. Okay, we just lobbed off the part of that sphere. Okay, let's see where we can go from there. That would tell us, by the way, that would tell us, if you will, that this bottom position, now let me expand this again so that we can see it. So I'm going to blow it up a little bit more, okay, just so we have something to work with. And let's talk about, this is that, where the base is, and this is the top of that part of the sphere, okay, the top of the cap. And so as we imagine this going out like this, okay, and then it has this, okay. Now, remember this value is the y value of r, and this value is actually, see, this value right here is r minus h, because this distance right here is h. And the whole distance is r. Okay? So what I'm going to be doing is I'm going to start these frustums. Okay, so here's the surface area. We're going to integrate from the lowest value of r, x of y, which is r minus h, to the highest value of y, which is r. And remember, the frustums are starting at this level, and they're going this direction. Okay, so that's from r minus h to r. Now, when we look at a circumference in one of these, so again, I need to come down here so I've got this stuff kind of cleaned up. Okay. Now, I'm looking at a circumference, let's do this, okay, I'm looking at a circumference of a frustum. So I'm looking at the circumference. So this distance right through here is my circumference. Oh, and that's an x value, isn't it? That's an x value. Okay, and it's x equal to, well, what do we have to work with? We've got the information that the way out to the edge of that sphere, the points on that sphere are given by this. So x, and that's a positive value of x, is the square root of r squared minus y squared. So that's actually that's not the circumference, my bad. That's the radius, isn't it? My bad. You're probably wondering, what in the world is that guy thinking? So the circumference is going to be 2 pi times the radius. And so in here, remember, it's going to be circumference times arc length. That's what we're going to integrate. Now, we already have our limits of integration from r minus h to r. Circumference is 2 pi times the radius. And the radius is x, which is the square root of r squared minus y squared. And then the arc length in this case, remember, is measured this direction. And so we've seen that already. That's the square root of of 1 plus g prime of y. See, this is x, or g of y. Okay, and in here we have g prime of y. Okay, we need a g prime of y, which could be written as the derivative of x with respect to y. That's the same as g prime of y. And so we look up here and we're taking the derivative of this with respect to y. So I'm going to write it as derivative of x with respect to y, and that's squared, and of course dy, because we're moving y values. Okay, well, now, if x is equal to the square root of r squared minus y squared, then the derivative of x with respect to y is the derivative of that square root. And the derivative of that square root will be 1/2 times r squared minus y squared to the power negative 1/2 times the derivative with respect to y of the insides, which is negative 2y. Now when we square that, and notice the 2's are going to go out, aren't they? And so actually that ends up, let's go ahead and clean that up, that's negative y over the square root of r squared minus y squared. So when we square that, we'll actually get y squared over r squared minus y squared. Okay, now on the next page I'm going to write this down, and we're going to keep this in mind. And so we know how we're going to set it up. This is the surface area calculation right here. This is the surface area calculation. So we just need to be able to, and remember that's of the cap, so we just need to be able to calculate that integral. Okay, as we saw, the surface area of that cap is the integral above. But we know that derivative of x with respect to y squared is, with respect to y, that derivative squared is y squared over r squared minus y squared. That's from the previous page. So the surface area of the cap a spherical cap. I still have some work to do, but we're getting close. Is equal to s, which is this integral, from r minus h to r of 2 pi, to r of 2 pi times the square root of r squared minus y squared times the square root of 1 plus this fraction, which is y squared over r squared minus y squared, dy. Now, under the radical, see, under this radical, I'm going to write 1, so we're going to take 1 and write it as r squared minus y squared over r squared minus y squared. And when we do that and add the two fractions together, you see that we'll have the y squareds go out. So this integral, by the way, let's factor the 2 pi out. So we've got a 2 pi times the integral from r minus h to r of the square root of r squared minus y squared times the square root of a fraction here. And the fraction, the numerator will be r squared minus y squared plus the y squared of the second fraction, so we end up with r squared only divided by the common denominator of r squared minus y squared with respect to y. Well, look what's going to happen is that we're going to have, as we think about dealing with a product of radicals, and that's what this is. So we have 2 pi times the integral from r minus h to r. A product of radicals is the square root of the first integrand minus the second integrand. And of course, what do we have happen? We have that denominator cancel. So we're left with the square root of r squared. And of course, r is a radius, so that's a positive number. So we end up with 2 pi times the integral from r minus h to r. And the square root of r squared is just r. And we're doing that with respect to y. Well, the integral of r, which is a constant, remember r is the radius of the sphere, and so it's just a constant. Well, the integral of a constant is the constant times the variable, and we're going to evaluate that from r minus h to r. And those are the y values, remember, those are y values. So as we calculate, we get 2 pi. When we put r in for y, we get that. Minus, now we're going to put in, we're going to put in an r minus h. I'm having trouble writing. R minus h for y. And I think as the smoke clears, here we'll have an r squared. And here we'll have a negative r times r, which is minus r squared, but we'll have a negative r times a negative h, which is plus rh. And you see the r squareds go out, and we're left with 2 pi times rh. Remember, this is the surface area of a spherical cap. Now let's recap what we're talking about. We had a sphere that we began with, okay? And we just put it on a coordinate axis to make it easy for us to calculate, to think about this. So here, that's just to represent the fact that we've got a sphere. And we know that the radius of that sphere is lowercase r. Now, what we're wanting to do is we're wanting to lop off part of that sphere. So you just take the top part of that sphere, lop that off. And that's the cap, okay? And so that cap, this is what we've got down here. That cap looks like this. Now, this radius we don't know, but we don't need to know it. All we need to know is the radius of the original sphere, and we have that. And then we need to know how high it is from the base of this cap to the top of this cap, and that's h. So that's where we get the r over here. That's the original radius of the sphere, of the original sphere, and that h is how high the cap itself is. And that will be the surface area of that cap. Well, I think I've given you enough examples. You're going to have to experiment, of course, on your own, and that's going to be some work, obviously. Some of the problems are easy, and some will take quite a bit of concentration. Good luck to you. I hope this has been useful.